Welcome to Numerics. The purpose of this presentation is to set up a geometry in SpaceClaim, take it over into PumpLinx and run a simulation, then come back to SpaceClaim to modify the model, and then resume the simulation using the modified geometry in PumpLinx. This is the liquid volume, which has been split out from the solid parts like the pump housing, impeller blades, and so on. Before we go over into PumpLinx, we can take advantage of some of the features in SpaceClaim to make the model setup easier in PumpLinx. If we name the surfaces that require boundary condition specification here in SpaceClaim, then we can skip the surface preparation steps in PumpLinx. So the components to our model are basically this. This is the impeller, and here's the volute. So first we're going to name these surfaces. This is an outlet. It's already been named, but I can show you if you want. You can change this name here. This is an inlet. And these side surfaces here are called MGI surfaces. The MGI surfaces stands for match grid interface, are necessary for the two fluid volumes to communicate with each other. Likewise, the volute also has an MGI surface. Another thing we can do is to pick a volume and set the cell size so that we can control the mesh refinement level here. So here you have the cell size on the surface and the maximum cell size, so you can control the refinement level. The geometry here has been set up and identified so that we can now take this into PumpLinx. So we'll launch and mesh this in a single operation. You see you have a few options here. We'll choose Launch Numerics and Mesh. Give it a name. The loading process takes a minute or so, so I'll skip over that. So here's the model that was imported into PumpLinx. And since we don't need these CAD surfaces anymore, since we already have a mesh here, I'll expand this out so you can see what boundaries comprise this mesh. And let's take a quick look at the mesh. We'll put a Z cutting plane here. And you can see here we have a very nice grid. Now you can see over here in this mesh panel, there's quite a few tools available to the user. But since we already have a good mesh here, we can just close this to make room for some of the other panels. Now the first thing we need to do is select the module that we'll be using for this simulation. In this case, we'll be using the Centrifugal template, and also we'll use the flow module, and we'll include turbulence and cavitation. This cavitation module performs cavitation and aeration, very useful for these pump simulations. So now we have the modules that we're going to use, and let's set up the centrifugal template first. Here it's in template mode. If we wish, we could turn it to extended mode where it'll show many more options if needed, but for simplicity we'll just keep it in template mode for now, and we'll be running a steady state multi-reference frame simulation. And the number of blades here, you can see we have 6. That's for timing purposes. The rotor center is at the origin. That's good. Rotation direction is clockwise, and we'll say it's 2000 RPM, and the axis will be in the Z direction. Now let's have a look at our fluid properties. You can see it's water. All the properties look right, so the default works out very nicely here. Now we can begin assigning boundary conditions. So the first thing I'm going to do is connect the two MGIs via connect selected boundaries via MGI. So that's connected now. Now let's assign our inlet conditions. And you can see it's a very short list here, which makes it very easy to select boundary conditions. Although if you wanted to, you could expand this list to have more options if you wanted. But this makes it very quick and very painless to set up these boundary conditions. And an outlet. This is a volumetric flow condition. Just put a value in here. So the inlet and the outlet are set up, and the MGIs are set. So the only thing left is the impeller wall, which will set as a rotor. And you can see the rotor parameters are the same as what was specified in the centrifugal template. So all the information was transferred automatically over to this rotor boundary condition. So you don't have to do anything. Very convenient. Now I'm going to add in a monitoring point so that we can monitor the fluid properties at any point in the model. In this case, I want to point right at the edge of the blades here. And I'm going to plot this. And this is how you set up a plot. So now let's start the simulation. I'm also going to put another couple of plots in here. Here I'm going to monitor the total pressure at the inlet. So now I have the pressure at the inlet and the pressure at the outlet. This way you can see what the pressure difference is across the device. So we can see the pressure, as you can see, the pressure at this periphery of the rotor is beginning to look constant. So the solution is almost converged. And I've added in a third plot so you can see the power that it takes to run this pump. So as the solution is converged, we can take a look at the flow field. This is velocity magnitude. We can look at vectors. We confirm that it's spinning in the correct direction. Let's have a look at total pressure. Everything looks reasonable. Now let's return to space claim, and here I'm going to modify the geometry. And now that I've modified the geometry, I'm going to export it back into PumpLinx and resume the simulation. So I'll go into Simerics, and this time I'll choose Replace Project Geometry. So here is a modified model. You can see the volute outlet here has been extended. So let's check our conditions, and we can see that the boundary conditions are still in place. So we simply replace the geometry, and you can do this as long as you retain the same topology. So we can go right back into the simulation and begin again as before. So in this way so this is an example of how this can be used as a design tool. It's very easy to use, and you can very quickly develop models and optimize your designs.